I am going to introduce a very interesting and uncommon topic, that is toppling. Maybe you are not familiar to this topic as it is not included in NCERT book, but it is there for syllabus of JEE and NEET. So let us see what is this toppling and how numericals are solved based on this. Let's get started. I am going to start very interesting thing, that is toppling. But before seeing what is toppling, one natural phenomena which is shifting of normal reaction has to be learned, that what is this shifting of normal reaction and why do this occur. So let us consider when a surface comes into contact with another surface. Here I am writing a block which is placed on a surface, then of course the surfaces will apply normal reaction on each other. Have you ever thought of where this normal reaction is exactly applied, at which point is it applied? We do not know anything about this, but we never think about this. But actually this normal reaction is not applied at any particular point. It has to be distributed all over the surface. Though while drawing, we do draw at a single point, that is through the center, the location of normal reaction, but actually it is distributed over the whole surface. Now if you consider a uniform block which is lying on the horizontal surface and normal reaction is distributed over the whole surface, but if it is in translatory or in rotatory equilibrium, then we have to write net force to be 0. And let us see how the net force can be equal to 0. How can we write this? Because weight has to act through the center of block, that is mg. So for translatory equilibrium, easily we can write n to be equal to mg. But while writing the equation for rotatory equilibrium, we have to write net torque on the body to be 0. To balance the torque and the force of gravitational pull, normal reaction has to be applied at its center, because then only its torque will be equal to that of the torque of weight about any other point. Otherwise, if we draw its location of normal to be at any other point, then it will be having an effective torque and it cannot be in rotatory equilibrium. So for rotatory equilibrium of the body, we have to draw normal to be passing through the center of gravity itself. And this is the reason for which we do draw normal reaction to be acting at the center of gravity itself without thinking about why we are drawing like this. So this is the reason you can see here. Now I am going to consider few cases where we will see that how this shifting of normal occurs and why does this occur. So let us see one example. A uniform square block of side A and mass m is lying on a horizontal surface. Let us draw this. It is lying on a horizontal surface. Side length is given A and its mass is m. Of course, we have to draw weight, that will be equal to mg. Now another block of mass m is placed on the top corner of the block. I am putting this another block here which is also having the same mass m. Find the distance by which normal reaction is shifted. Let us first see, is there any reason for normal to be shifted? So first consider our normal to be acting through center of gravity itself. But if it is passing through center of gravity, weight also is passing through gravity, then for normal reaction which will be applied on the lower block due to the upper block and its value being equal to mg, it will start producing a torque about any other point. And so this body cannot be in rotatory equilibrium. Now do remember that this is natural phenomena, that always a body tries to be in equilibrium if it can do it. So for this to be in equilibrium, normal has to shift its position. And we cannot draw normal through the center. So now let us displace it to other position. Here I am drawing normal at this location, which is at a distance x from the center of gravity. First, I am going to write translatory equilibrium, for which n has to be equal to n dashed plus mg. As we know that n dashed itself is equal to mg, so directly we can write n to be equal to twice of mg. And what about rotatory equilibrium? Now we have to write torque. We can write torque about any point, but it will be easy, as I had said earlier also, if you write torque about any point on which a force is acting, then at least one of the torque will be removed. So let us write about O, which is the center of block. We can write net torque to be equal to, now see, this N is producing a torque in anti-clockwise direction about O, whereas N dash is producing a torque in clockwise direction about O. So if it has to be in equilibrium, these two torques has to be equal to 0. Let us write the torques first. For N, torque has to be equal to N multiplied with X. And for N dashed, it has to be equal to N dashed A by 2. Since upper block is very small, so its dimension can be neglected. Now if I substitute the values, 2 mgx minus mg A by 2. Now on solving, this will give x to be equal to A by 4. So on putting the upper block on lower block, the normal got shifted to a distance A by 4 towards right. And always this normal has a tendency, because it is a self-adjusting force, so it will have a tendency to shift to a position so that to minimize the effect of any external torque which causes the body to topple. One more example here I have for shifting of normal. So let us see this. A cubical block of side A is held at rest against a rough vertical wall by applying a force F acting along the center. One block we have to draw against the wall, and F has to be applied like this. Of course, weight will be there passing through center and in vertically downward direction. Again, one normal has to be drawn, which will be normal between the wall and the block, and for the block it has to be in upward direction. Now at what position it has to be drawn? So let us draw this normal to be here. I have considered so that the block can remain in translatory as well as rotatory equilibrium. Is there any force missing here? Of course, because the rough vertical wall is there, so one friction will be also present, which has to be in upward direction. As we know that due to weight, the block will have a tendency to slide down, so a friction has to be there in upward direction. Now we have to calculate first minimum coefficient of friction between the block and the wall. Let us solve this first. Since the block is in horizontal equilibrium, so we can write F to be equal to N and also F to be equal to mg for vertical equilibrium. But as we know, I am doing the first part, as we know that F has to be less than equal to mu n, so it has to be less than equal to mu f, or we can get mu will be greater than equal to mg upon f, because f is having value mg here, so mu has to be greater than equal to mg by f, and we can write minimum value of mu will be equal to mg upon f, which is our part 1 solved. In next it is asking torque by normal reaction about the center of mass. For this we have to calculate all the torque about center of mass, and since it is not in rotation, so it has to be equal to 0. Now let us consider this point being O. We have to write for the second part net torque about O has to be equal to 0. And what is this torque? If we are writing torque of normal to be equal to tau n, another torque has to be due to friction, because F is passing through center of mass itself, so it will not produce any torque. mg also is passing through the same point, it will not produce any torque. We have to write only torques due to normal and the friction, and torque for friction has to be equal to minus Fs A by 2. This length being A, its center of mass has to be at A by 2 from the wall. I have put a minus sign here because normal will have a tendency to rotate it in clockwise direction and friction will have a tendency to rotate in anti-clockwise direction. That's why one is positive, other is negative, and this should be equal to 0. From here we got torque of normal to be equal to Fs A by 2. Again you can see that normal has to be shifted to position other than center of mass so that net torque on the block can be written as 0. And this is the cases of shifting of normal whenever an external torque is there which will try to rotate the block or rotate the body. Normal will shift its position and will try to minimize the effect of external torque. The other thing is toppling. Of course, normal will have a tendency to minimize the effect of external torque, but what if it cannot fully cancel that effect? Then it causes toppling. Again, if you consider a square plate which is put on a horizontal surface and consider that a force is being applied at the upper surface like this. Weight has to be here through the center. Let us consider this corner being A. Now normal reaction will shift to balance the torque produced by F, and as you can see here that this F will try to rotate about A in clockwise direction, so normal has to be shifted towards right so that it can produce a torque. Now normal reaction will shift to balance the torque produced by F and friction about center of mass. Now if force F increases, of course, then normal will shift further and further, but shifting of normal has a limit. It cannot go beyond A. So if F is further increased, then normal cannot shift further to balance the torque, and hence now the block will start rotating about the point A, which is called toppling. So this normal can be shifted only up to point A. It will continue shifting till it reaches point A, and then after that, if still torque is not balanced about A, then the block will or the plate will topple about A. This is called toppling. Let us consider one case, one example based on this toppling. A square plate of side A and mass M is lying on a horizontal floor. Let us draw this situation. A force F is applied on the top. I am considering the same situation. Find the maximum force that can be applied on the square plate so that the plate does not topple about this corner A. Now let us first draw all the forces on the plate. Its weight has to be here, and then one friction, because due to this external force the plate will have a tendency to move towards right, so a friction has to be there towards left. This is the friction shown here. Now first normal will be shifted, and it will be shifted towards right to minimize the effect of torque due to F. But till which point it can shift? It can shift to A, and this is the maximum shift for the normal. So let us consider that normal has already been shifted to the point A. Now if it is in equilibrium, then we have to write N to be equal to mg and friction to be equal to F. But for rotational equilibrium, if we have to write torque about any point, though we can write, but let us consider about O, then torque about O, if we have to write to be 0, it should be equal to F A by 2 plus F A by 2 minus N A by 2. Here I have considered that normal has been shifted fully to A, and as you can see that friction and external force F both will try to rotate the plate about O in clockwise direction, whereas normal has tendency to rotate it in anti-clockwise direction. So for one direction I have written positive, for other it has to be negative. This implies that FA will be equal to mgA by 2, which on solving will give F is equal to mg by 2. This is the maximum force for which the plate will not topple about A. If F is increased by this value, then it will start toppling about A, because normal now cannot balance the effect of torque produced by external force and the friction. So this is the case of toppling, and very good questions can be asked from this subtopic. One more example I have related to toppling. A force F is applied at the topmost point of a cylinder of radius r and height h. If the cylinder remains at rest, then find distance of line of action of normal reaction from center of mass. This is something from shifting of normal. And then in next part, we have to find coefficient of friction required so that the cylinder topples before sliding. This is very interesting case. We have to consider both toppling and sliding, but it has to be toppling before the sliding. Let us first draw the situation. Let this be the cylinder of height h and radius r. Height is given h. This be the axis of cylinder. Its radius is given r. Now if F is applied like this, which is at the top of cylinder, then we have to consider its translatory as well as rotatory equilibrium. So let us draw all the forces. Weight has to be acting in vertically downward direction through the center. Again, let us consider that normal has been shifted towards right by a distance that is equal to A. This shifting I have considered as A. Of course, friction will be there in this direction F, so as to oppose the external force, and it has to be numerically to be equal to the external force F. Now for writing equilibrium condition, first we have to write F to be F, which is already I have shown here. And for rotational equilibrium, if I write net torque about center to be 0, let us take this as O, then what the torques will be there? F into h by 2 plus, now for friction also I am writing the same magnitude, that is F into h by 2 minus NA. As you can see here, both external force and the friction are producing torque in clockwise direction, whereas normal in anti-clockwise direction. And since we are writing torque about O itself, so there will be no torque for the weight, and this has to be equal to 0. Now on solving, we will get value of A being equal to FH upon normal, and normal, as you can see, can be written as mg, so it will be equal to FH by mg. So this is the value of shifting, which is our part 1. Now for this next part, we have to consider toppling. So about which point it will topple? Of course about this corner, let that be A. So if we write toppling about A, then for this to topple, we have to write that torque of F should be greater than torque of mg, right? Because if we are writing torque about A, then there will be no torque for friction, and N, since it is the case of toppling, so will shift to position A. Again its torque about A will be 0, and then we have to write torque of F has to be greater than torque of mg. What is torque of F about A now? It can be written as F into h, which should be more than mg r, because its radius is given r. So from A, the distance of center of mass is r. From here we got the condition that F should be greater than mgr upon h. Now if it is to avoid sliding, F should be less than mu mg, because if external force is less than the limiting friction force, it cannot start sliding. So now we have both the conditions. For toppling it has to be F greater than mgr by h, and for sliding it has to be less than mu mg. From here we got the condition that will imply r by h should be less than mu. So this is the value of mu required if cylinder has to topple before it starts sliding, which is our part 2. One more example I have related to toppling. A uniform cube of side A and mass m rests on a rough horizontal table. Let us draw this situation. Here the surface is rough. Edge length is given, that is equal to A. A horizontal force F is applied normal to one of the faces at a point that is directly above the center of the face at a height 3a by 4 above the face. So here point of application of force is like this. It is at a height 3a by 4 above the base. So this is application of force F. The minimum value of F for which the cube begins to tip about the edge is, of course, with application of this kind of force, it will topple about the point which is shown O here. Let us calculate what should be the minimum value of F. Now for minimum value of F, the torque of F about point O has to be equal to, because weight has to be at the center, that is mg, and as we know, to minimize the effect of toppling, normal shifts to this point. So if we write net torque about O, then it has to be equal to 0, because we are considering just the limiting condition, and this will lead to F multiplied with what is the perpendicular distance with O? 3a by 4. So F into 3a by 4 has to be equal to mg, and then perpendicular distance with mg is, this has to be equal to a by 2, so a by 2. From here we can write value of F to be equal to mg a by 2 into 4 upon 3a. These two got cancelled. So we got finally 2 mg upon 3. This F I have calculated for the limiting condition where the net torque about O is 0. So if F exceeds this force, it is just the limiting value. If F exceeds this value, then it will start toppling about O. So this is the minimum force required. F minimum can be written as 2 mg upon 3. Today we discussed very interesting subtopic, that was toppling and shifting of normal, and in coming session, in next session, now I will teach you about work done due to the torque, also power developed due to the torque, because already we know the torque, and as in case of translatory motion, after knowing force, we can calculate work done due to force and power developed by force. So here also in rotation, these are the analog terms. So we will see how is work and power calculated for torque. Until then, you have to practice few questions based on the current subtopic, that is toppling. You will get very good questions from this subtopic. So please do remember that you have to solve at least 10 questions from each subtopic, so that you will be comfortable solving different kinds of situation if it arises from any particular subtopic. So let us keep practicing more and more number of questions, and this is the only way to crack your JEE or NEET exam. There is no shortcut, only you have to solve more and more number of numericals to get into medical or engineering colleges. So, best of luck for your future and keep practicing. Waiting for the next session. Bye.